So my name's Charlotte. I'm the CEO of Chemtrix. We're a continuous flow reactor company based in the Netherlands. And our focus in the Nefertiti project is to design a continuous flow reactor for a photocatalytic application. So within this session, we're going to look at why we use flow reactors, what they are, the benefits of them, how you use them, and specifically focus on light-activated processes, the incorporation of photocatalysts, and what's important when you're designing a flow reactor for photocatalytic processes. And at the end, we'll give you a summary of the integrated system that we're developing within the Nefertiti project so that you can see how the flow reactor fits within the total system. So compared to batch reactors, which you might be more familiar with, continuous flow reactors are tools that are used for either screening at the milligram scale or manufacturing up to several hundreds of metric tons per month. So compared to a batch reactor that you can treat as like a coffee cup, where you would be stirring your materials, we continuously pump material into a flow reactor and continuously collect it from the outlet. This gives the advantage that the reactors are much smaller than a batch vessel, and you can use them for increased process intensification and increased sustainability when designing safe, scalable chemical processes. So in the picture here, you can see small lab equipment within the hands of my colleague Max, all the way through to production equipment that can be several meters in size. So just because they're continuous doesn't mean they're not able to produce large amounts of material, but you do go through from lab to production with these pieces of equipment. So reducing the size of the reactor has a really positive impact on processing, and it's generally down to the fact that you have a higher surface to volume ratio compared to a batch vessel, and this helps with heat transfer, mass transfer, and safety. It also gives a high degree of reproducibility because you're constantly running under the same conditions, and it helps you to very successfully scale your process without losing benefits such as improved thermal control and short reaction times. So here you can see some examples of why people would use flow reactors, typically energy-intensive processes, unstable intermediates, and in our case, where we would like to incorporate efficiently light into a reactor. So if we compare to a batch process, you'll typically have a vessel containing your reaction mixture, and over time, you will see that that reaction mixture changes and you have conversion of your reaction product. So if you want to start a new reaction condition, you have to empty it and start again. In comparison, a flow reactor, at the beginning of the reactor, you have essentially T0, no reaction, and at the end, you have complete reaction. So it's spatially controlled as opposed to time controlled, and you can see that in the graphic here. If you were to stop the process in the center, you would have half your conversion. So in comparison to a batch process, you can really quickly optimize a process. You can be changing parameters on the fly, and that allows you to more quickly and more efficiently optimize a process. So if you've never seen a flow reactor before, compared to a batch reactor, it's quite different. You can see in the schematic at the bottom of the screen here that we typically have pumps, so we're constantly delivering fluid into the reactor. We have a reactor vessel itself, so this could be a tube, a plate reactor, a coil. It's thermally regulated by putting it into an oil bath or by having a continuously circulating fluid, and then we're constantly collecting the product. So over a period of 8 hours, you would constantly collect material, unlike batch, where you may run it for 8 hours and then empty the tank, and that gives you your product. So key is selecting the right material of construction. Does it need to be transparent? Does it need to be pressure resistant? You need to decide how you're going to activate. Are you going to heat? Are you going to put light in? How many materials do you add? And how much material per hour do you want to generate? And these are all considerations that we put into play within the Nefertiti project to plan the reaction mixture and also plan the size of the reactor. So because of this scale reduction, benefits of flow chemistry are safety, reduced development time, improved process control, and reduced production costs. Not all chemistry gets all of these advantages that you can see on the screen, but it depends on what your process challenge is as to which of these advantages that you can expect from your process. So particularly within the Nefertiti project, we're focusing on light activation rather than heating a process. So we have a photocatalyst within the device, and we need to actively get light into the reactor so that we have efficient photocatalytic transformation. Now, when you scale a photochemical process, the most important part is that you can get light well into the device. And as you can see in the schematic, as you're putting light into a device and the volume of that reactor changes, you get less efficient light in coupling. And this means that you have a failure to scale, or a process that the lab doesn't go through into production. So what we hope by using continuous flow reactors is that we're working in this very short path length section of a reactor, and that means that you're always efficiently getting light into the device. And if we compare this to what you see on the screen now, a batch reactor, you can see you have very low efficiency of light in coupling. So by having a short path length, the light passes all the way through the reaction mixture and activates the material well. So here on the screen you can see that within the Nefertiti project we've designed a glass flow reactor. So it's completely transparent with integrated thermal control, and we have a really high surface to volume ratio so that we're able to irradiate thin channels of fluid very efficiently. We also have surface channels that we pass a recirculating thermal fluid through, and this allows us to thermally regulate the mixture. We're also working with NUIG on the incorporation of a photocatalyst, and this can either be done as a solution, as a wall coating, or a packed bed. And here you can see graphics showing you how that would work within a continuous flow channel. Within the Nefertiti project, we're specifically focusing on wall coating with a view of having a ease of incorporation, maintaining the transparency to the light, and also having a low pressure drop so that we can pass a large amount of gas through a single device. And of course, if we're going to use light, we actually need a very efficient light source. So the final part of that photochemical setup for us is that we can irradiate the reactor. Now, typically you would do this either with an artificial light in the form of a xenon lamp or LED arrays, but within the Nefertiti project we're using sunlight, either direct or via solar concentrators. And the light source power will very much depend on whether or not we use lenses, which you will hear about in other chapters of this MOOC. So in our project, we're specifically using solar irradiation with photosensitizers on the outside of the process channel, and you'll hear more about this in chapter 9. So here you can see the final concept of the reactor. We've got gases coming into the reactor. We have a photocatalyst on the internal channel. We have a photosensitizer on the outside of the reactor. And when operating this continuously, we can then generate the reaction products continuously and feed them into the next part of the continuous flow system. So here you can see the integrated total system within the Nefertiti project. We have 2 flow reactors operating 2 different photocatalytic processes. We have an absorbent system in between for oxygen removal. And at the end, we have a membrane purification for the C2+ alcohols that are generated within the reactor. And what you can hear more of in the upcoming sessions is how this will be integrated into a total system by our partner SOCA, and how the other partners fix together their elements of the continuous flow reactor. So my name is Charlotte, and as part of this project, we've been looking at the photochemical development of a light-encoupled transparent flow reactor. Thank you for your attention.